So this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know for your upcoming test. So we'll start with statistics and then get on to probability and finally index laws. So let's look at statistics. So let's say I have these set of test scores. So what I'm going to do first is put this into a stem and leaf plot. So you've probably done this a million times. So to set it up, you need a stem. So that's basically the number of tens, and then the leaf is the number of units. So we're going to divide this into scores in the 60s, 70s, 80s, and 90s. So we're going to put all the scores in this stem and leaf plot in order. So we just put an 8 here. That score means 68. That's the first one done. And we do similarly for the rest of the scores. This is what our stem and leaf plot looks like. It's just a convenient way to display data. So from the stem and leaf plot, we can comment on the skewness of the data. So what we note here from the stem and leaf plot is there are more scores closer to the maximum, which is 99. So we're looking at the definitions below. We say our data is negatively skewed. That doesn't necessarily mean the scores were higher. All it means is that there were more scores closer to the maximum, closer to this score 99, than there were to the minimum or the middle. So a stem and leaf plot's basically a histogram on its side. If we were to draw this as a histogram, it would look like this. Remember, a histogram lists the score along the horizontal axis, and along the vertical axis is always frequency, how many times the scores occurred. So higher bars mean that score occurred more often. So you can see from our histogram here that there were more scores in the 90s, and there were fewer scores down here towards the minimum in the 60s. So that's what a negatively skewed histogram looks like. Positively skewed histogram looks the other way. We'd have higher bars down this end and lower bars down this end. And symmetrical, we'd have the bars highest in the middle. Just draw an example of what a symmetrical and positively skewed histogram look like. Just be a bit careful because it sort of goes the opposite way that you'd expect. You'd expect more high scores if it was positively skewed, but it's the opposite. More high scores means it's negatively skewed, more low scores mean it's positively skewed. All right, now I'm just going to rub down the bottom of this slide and we're going to calculate mean, median, and mode. So we'll start by calculating the mode of this data. The mode is the easiest to calculate because it's the most common. Now you see in this data set there are two scores that occur twice, but none that occur more than twice. So it turns out there are two modes, 83 and 94. So when there are two modes, we say that this is bimodal. So this set of scores, in addition to being negatively skewed, is bimodal because there are two modes. If there was one mode, we'd say it's unimodal, and more than two modes, we'd say that it's multimodal. All right, that's all for the mode. Let's now calculate the median. Remember, when you're calculating the median, you need all the scores in order. Well, that's one good thing about the stem and leaf plot. We've already put our scores in order. Now, there are an even number of scores. There's 10 scores, which means there will be two middle scores. We need to find the point where there are the same number of scores above the median as below it. So if we highlight these two here, note that there are 4 scores above that, and there are 1, 2, 3, 4 scores below. So we have two middle scores. Now, when you have two middle scores, what you do is simply add them up and divide by 2. You take their average. So the median of these scores will be 83 plus 88 over 2. Note that these scores here are not 3 and 8, they're 83 and 88. So if you put that on your calculator, you just get 85.5. So here the median is 85.5. Remember, even number of scores, there will be two middle scores and you take their average. If there's an odd number of scores, then one of the scores will be the middle. So let's now calculate the mean. So the mean, which a lot of people call the average, you just add up all the scores and divide by how many. So the scores add up to 858. We divide by 10 because there are 10 scores. The mean is 85.8. So in addition to being able to calculate the mean like we just did, we need to be able to use the mean to find a score. So I'm saying I'm going to take these 10 scores, I'm going to add another score to it, and the new mean's going to be 86. So what's the new score? So we know that the mean, which I'll just call x by here, is equal to the sum of the scores divided by how many. So rearranging this formula, if you take the mean and times it by n, the number of scores, you get the sum of scores. So how does that help us with the question? Well, I know if I add another score to the ones above, I have 11 scores. So if the mean of those 11 scores is 86, then the scores must add to 11 times 86, which is 946. So before I added the score, they added to 858. After I add the score, they need to add to 946. So the new score is simply going to be 946 minus 858, which is of course equal to 88. So the new score must be 88 so that the mean will become 86. All right, that's all for statistics. Let's now move on to probability. Probably know by now that probability is the assigning of a number to a random event. We give a random event a number to indicate how likely it is. So whenever you're asked what is the probability of something, you need to give a number between 0 and 1. The closer it is to 1, the more likely it is to happen. So let's look at this question here. We have class 30 student, 8 with blue eyes, 10 blonde hair, 17 neither, and we're going to select a student at random, find the probability they have blue eyes but not blonde hair. So this is a complicated question, and it involves two sets. We're talking about the set or the group of people with blue eyes and the set or group of people with blonde hair. Of course, a student could be in one group, both, or neither. They could have blue eyes only, blonde hair only, both, or neither. So when we're dealing with two categories, we use Venn diagrams or two-way tables. They do exactly the same thing, they just display the information in a convenient way. Now you need to be familiar with both. So just for ease of notation, I'm going to let A be the set of students with blue eyes and B the set with blonde hair, just so I can refer to them as A and B rather than always saying blue eyes and blonde hair. So let's start by drawing a Venn diagram. So Venn diagrams always look the same. They have a rectangle, and in it they have two circles that represent the two sets that we're talking about. So one of them is going to be A, blue eyes, one of them B for blonde hair. A two-way table always looks like this. So for the two-way table, it is a 4x4 table, but there are two ways. One way is A, or A dash means not A. Then B or not B is the other way. So these four numbers in these cells here, they're the same as the four numbers that go in the Venn diagram, and they correspond to the four possibilities that I mentioned before. Student can have blue eyes only, blonde hair only, both, or neither. So one thing that's different about a two-way table is it has a row for totals, which the Venn diagram doesn't. So let's now fill in these numbers. Now you might be a bit worried thinking, wait, 8 plus 10 plus 17 is 35, but there were only 30 students. How can this possibly be? Well, the only way they can add up to 35 is if I've double counted 5. If I've counted 5 students in the blue eyes group and also in the blonde hair group. So however many you've overcounted goes in the middle of the Venn diagram. However many you've overcounted is how many are in both. So there are 5 in both. So that goes here and here. So let's look at the Venn diagram now. We want to fill out the number that have blue eyes. There's already 5 in the A circle, so we need another 3. We don't put 8 there, because if we put 8 there, there'd be 13 in the blue eye circle. So similarly, blonde hair, there are 10 of them. We already have 5 in the B circle. We need another 5. And the 17 that have neither go outside the circles. So when we look at our two-way table, so this number here is A and not B. So those 3 go there. Here we have B and not A is 5. And then neither, not A, and not B is 17. So we might just fill out the totals for the two-way table as well. So note, in both cases, the numbers should add up to 30. So note 3 plus 5 plus 5 plus 17 does equal 30. So we know we've done something right. And similarly for the two-way table, these 4 numbers add up to 30. So once we've put this information in a two-way table of Venn diagram, it becomes really easy. What's the probability a student has blue eyes but not blonde hair? Well, there's 3 of them from here, and we can also see that here. There are 3 people with blue eyes but not blonde hair out of 30 in total, so the required probability is 1 over 10 or 0.1. So we can write this in set notation. This is the probability of blue eyes and not blonde hair. Okay, so make sure you know these symbols. Remember, this one here means and this one here means or. So A and B just includes those in the middle of the Venn diagram, people that have blue eyes and also blonde hair, or includes all of the things in the Venn diagram, 3, 5, and 5. It includes these numbers here. So when we say the people who have blue eyes or blonde hair, we include everyone with blue eyes, everyone with blonde hair, and those that have both. So please make sure you know the difference. Now we're going to go on to tree diagrams. Let's look at this question here. A coin is tossed and a card is drawn from normal 52 card deck, and we want to find the probability I either get heads from the coin or hearts from the card. So note in the previous one we were looking at two categories, blonde hair, blue eyes, but we're only doing one thing. We were just picking one student at random. Here we're doing two things, tossing a coin and drawing a card. So this is something that occurs in stages, 2 stages, coin toss and drawing a card. When you have a multi-stage event, we use tree diagrams to list all the possible outcomes. So we set it up like this. So the first stage, the first thing we're doing, and the second stage. So for the first stage, we can either get heads or tails from the coin. So for the second stage, we list what we can get from the cards. Now we don't want to list all of the 52 possibilities. Even if we had to write, ace of spades, ace of hearts, ace of diamonds, and then 2 of spades, 2 of diamonds, and all that, that'd take way too long. In this experiment, we're only interested in the suit. So we just write the 4 suits. So if I get heads the first go, I can get hearts. I'm just going to write hearts here, just so we know it's not heads, and then you can get diamonds, spades, or clubs. Similarly, if you got tails the first go, you can get hearts, diamonds, spades, or clubs. So there are 8 possible outcomes. And the tree diagram just allows us to list those. We have the 8 outcomes. Everything's really easy. Note that because heads and tails are equally likely, hearts, diamonds, spades, and clubs are equally likely, all of these are equally likely, they all have probability 1/8. So because we have the list of outcomes, we just go through and figure out which satisfy what we're interested in, heads or hearts. So if we go through, we've got all these are included because they have heads, and this one's also included because it has hearts. These 3 aren't included, they don't have heads or hearts. So there are 5 outcomes which satisfy heads or hearts out of 8 in total. How easy is that? Now we're going to look at the difference in tree diagrams between with replacement and without replacement. So let's look at this example here. So have a bag, 5 crunchies, 2 boosts, 3 Mars bars, and we pick 2 chocolates, one after the other. We'll calculate the probability that at least 1 Mars bar is picked. So once again, this is a tree diagram question because we're performing the experiment in 2 stages, picking 1 chocolate, then picking a second. Now, as it stands, there isn't actually enough information to complete this question. We need one additional thing to know whether it's with replacement or without replacement. After I take the first chocolate, do I replace it with an identical one or not? That will change the answer. So let's start with replacement, assuming that when I take a chocolate the first time, I replace it. So if I get a Mars bar the first time, I replace it with another Mars bar. So, with replacement, first time I can get a Crunchie, a Boost, or a Mars bar. That's the first go. Now, the second go, I can get exactly the same. If I get a Crunchie the first go, I can still get Crunchie, Boost, or Mars the second go, and similarly, Crunchie, Boost, Mars, Crunchie, Boost, Mars. Now, what makes this different than the previous example is I need to put branches here because the outcomes are not equally likely. When I pick a chocolate, I have more chance of getting a Crunchie than a Boost or a Mars bar. So when that happens, we need to write probabilities on the branches. I didn't do it in the previous question because that was an example of where all events were equally likely. So first go, I have 5 over 10 or 1/2 chance of a Crunchie. I have 2 out of 10 or 1 over 5 chance of getting a Boost, and 3 over 10 of getting a Mars bar. Now the fact that this is with replacement means I have the same chance of getting all of those things on the next go. So if I get a Crunchie the first go, I will replace it with another Crunchie. So there'll still be 10 Mars bars and 5 Crunchies. So the probability of getting a Crunchie second go is still 1/2. Boost is 1/5 and Mars bar 3/10. Similarly here, it's 1/2, 1/5, and 3/10. The probabilities are the same on the first and second stage when it's with replacement. So I list my outcomes again, just like I did in the previous question. So now I actually have 9 outcomes, but the probability of each of them isn't 1/9 because they are not equally likely. So how do I find the probability? Well, what I do is I multiply the numbers on the branches. So the probability of crunchy then a crunchy is a half times a half, which is a quarter. Probability of crunchy and a boost is a half times a fifth, which is 1/10. And I do this for the rest of them. So you might note here, for example, the probability of crunchy then boost is the same as boost and crunchy. Now all of these should add up to 1, otherwise I've done something wrong, and you can easily check that they do. So let's answer the question. What's the probability that at least one Mars bar is picked? Well, let's go again and find the ones where there's at least one Mars bar. So this one, this one, this one, and this one, as well as the BM, those are the 5 outcomes where there is at least one Mars bar. So all of the ones I didn't circle, the other 4, they don't have that. They don't have at least one Mars bar. So to find the probability of one of these happening, it's an or question. It's probability I either get this or this or this or this or this. You add their respective probabilities together. So I go 3/20 plus 3/50 plus 3/20 plus 3/50 plus 9/100. If you add up all those 5 numbers, you can do it on your calculator, you get 51/100 or 0.51. So that is the probability I get at least one Mars bar. So now we're going to do the same experiment without replacement. Please pause and copy this down if you need. So now we're going to find the probability that I get at least one Mars bar, this time without replacement. So that means if I take a chocolate the first time, I don't replace it. So if I take a crunchy the first time, for example, the second time there'll be only 4 crunchies and 9 chocolates in total. The diagram looks basically the same, there's just a slight difference which will change our answer. So the only difference is the probability is the second time around. So the first time I pick a chocolate, still 1/2 chance of a crunchy, a 1/5 for a boost, and 3/10 for a Mars bar. But as I said, if I pick a crunchy the first time, there's only going to be 9 chocolates left and 4 of them are crunchies. So I have to change this. This will now be 4/9. The probability of boost will change. There's still 2 boosts, but only 9 chocolates. The probability of a boost is 2/9. So I need to change all of these branches here. So similarly, if I get a boost the first go, there are still 5 crunchies left, only 9 chocolates, but there'll only be 1 boost left the second time. So it'll be 1/9 and then 3/9. And I do the same if I got a Mars bar the first go. So when it's without replacement, the probabilities at the second stage are not the same as they were for the first stage. So to calculate the probability of each outcome, the outcomes are the same. We still have the same 9 outcomes. But to calculate their probability, we still multiply the branches. We're just going to get different numbers. So for example, the probability of getting a crunchy then another crunchy is now 1/2 times 4/9, which is 2/9. In the last example, the probability of getting 2 crunchies was 1/4, which is 25%. Now it's 22%, 2/9. So the probability has changed slightly. And I do so for the rest of the outcomes. I just multiply the branches together. Probability of crunchy and a boost is 1/2 times 2/9, which is 1/9. And then for a crunchy, then a Mars bar, it's 1/2 times 3/9, which gives me 1/6, and so on. So once again, these probabilities should add up to 1, and you can easily test that they do. So once again, the probability at least one Mars bar is picked, it's the same 5 that are circled. I add up their probabilities again, just like I did in the previous example. The only difference here is I'll get a slightly different answer because all of these probabilities are different. So the probability of at least one Mars bar is 1/6 plus 1/15 plus 1/6 plus 1/15 plus 1/15. So if I add all those up, I get the required probability is no longer 0.51, it's now 8/15. So 8/15 is like 0.5333 and so on. The probability has gone up slightly. There's slightly more of a chance that I'll get at least one Mars bar if I do it without replacement. All right, now let's move on to index laws. So you hopefully know by now, if I have something like a to the power of 3, we call a the base, that's the thing being multiplied, and 3 is called the power or index. The index tells you how many times you multiply the base by itself. So this here is called index form. I write it out in expanded form, I get a times a times a. So powers tell you how many times you multiply the base. We're looking at index laws, laws involving numbers in the power. So these are the 7 index laws that you need to know. Let's go through them one by one. So the first one says when you multiply bases, you add the indices. For example, if I have x squared times x to the power of 3, you just keep the same base and you add the powers. 2 plus 3 is 5. The second one says when you're dividing bases, keep the same base and subtract the powers. So if I had something like y to the power of 12 divide y to the power of 4, it's not y to the power of 3, you keep the same base and you subtract the powers. You get y to the power of 8. Now if you have numbers as well as bases, do the numbers separately. So if I had something like 8z to the power of 5 divided by 4z, you go 8 divided by 4 is 2, z to the power of 5 divided by z, keep the same base, z is the same as z to the power of 1, subtract the powers, you get 2z to the power of 4. So the third rule says when you have a power and you raise it to another power, keep the same base and multiply the powers. So if I have something like a to the power of 4 to the power of 5, keep the same base, multiply the powers. So the fourth one says that anything to the power of 0 is 1 except 0 to the power of 0. So 0 to the power of 0 is undefined. 1 to the power of 0 is 1, 2 to the power of 0 is 1, 3 to the power of 0 is 1, and so on. So if I have something like 7 to the power of 0, it's just 1. If I have something like 7x to the power of 0, so x can't be 0, here only the x is raised to the power of 0 because of order of operations. So this would be 7 times x to the power of 0 is 1, which is 7. So anything to the power of 0 is 1, you just have to make sure you know what exactly is being raised to that power. Here only the x was. So the fifth one says if you have a product raised to a power, just raise the first thing in the product to the power and then raise the second thing in the product to a power. So if I have something like 2x to the power of 4, you raise 2 to the power of 4. 2 to the power of 4 is not 8, it's 2 times 2 times 2 times 2, which is 16. I raise that to the power of 4, 2 to the power of 4, I raise x to the power of 4. Easy as. So the sixth index law says if you're raising a fraction to a power, you just raise the top to the power and the bottom to that power. So if I had something like x squared over y cubed to the power of 5, so then I raise the top to that power, x squared to the power of 5, keep the same base, multiply the powers. Y cubed to the power of 5, keep the same base, and multiply the powers. So I just raise the numerator to the power of 5 and the denominator to the power of 5. So the final index law is regarding negative indices. So basically it's saying if you have a negative power, it goes to the bottom of the fraction. So if you have something like x to the power of minus 3, we just put a 1 on top, and on the bottom we write the thing with a positive power. So if I had something like 2z to the minus 7, the 2 has a positive power, it goes on top. Anything with a positive power on top, anything with a negative power goes on the bottom, but write it with a positive power. So if you had something like, let's say, 3a to the minus 3b squared c to the minus 4, anything with a positive power on top, so that's the 3b squared, anything with a negative power goes to the bottom, but written with positive power. Okay, so now we're just going to look at a few quick examples involving multiple index laws. So let's simplify this in index form. So we want to write it as something to the power of something. So note that 2 is not in the brackets here, so it does not get raised to the power of 6. So this, doing the brackets, I leave the 2 alone. A squared to the power of 6, power to a power rule. Keep the same base, multiply the powers, like this. And now I can multiply the top. So 2a squared times a to the power of 5, keep the same base, add the powers, and when we're dividing by a to the power of 10, leave the 2 alone, keep the same base, and subtract the powers. How easy is that? Let's look at another example involving multiple index laws. Let's try this question here that actually involves heaps of index laws. So let's start with the left-hand side. So the 3 is not in the bracket, so it's not getting raised to the power of negative 3, so leave it alone. So I keep the same base, multiply the powers for the other two. Now on the bottom of this fraction, the 3 is in the bracket, so it is getting raised to the power of 2, like this. Okay, now for the second fraction, to raise a fraction to a negative power, you simply flip the fraction and make it a positive power. But actually, because we're dividing, we need to flip the fraction again and make this a times. So now I'm going to take the second fraction, raise the top to the power of 2 and the bottom to the power of 2. And now I simply multiply the tops and multiply the bottoms. So 3a to the minus 6, now b to the minus 12 times b to the power of 6, keep the same base, add the powers, minus 12 plus 6 is negative 6. On the bottom we get 9 times 81, a to the power of 4 times a to the power of 4. So that will give us, so firstly we do 3 divides 729, gives us 1 over 243. So we do the numbers separately. So a to the power of negative 6, divide a to the power of 8. So you keep the same base and you subtract the powers. So that's a to the minus 14, the b to the minus 6 stays. Now to write this with only positive powers, because we have numerator with negative powers, they go to the bottom of the fraction. So this becomes 1 over 243, and we write them with a positive power, a to the 14, b to the power of 6. How easy is that? Very last thing we need to do is scientific notation. Please pause and copy this down if you need. Scientific notation is where we take a really large or really small number and write it as something times 10 to the power of something. So in this first box is a number doesn't have to be a whole number between 1 and 10, and in this one it does have to be a whole number. It can be positive or negative. And in a sense, numbers written in this form are easier to understand. So let's start with a really big number like this. So it's a really large number. It's not in scientific notation. We want to write it like this. So what we do is we put the decimal point at the end. We keep moving the decimal point until we have a number between 1 and 10. So if we move the decimal point, so we get a number between 1 and 10, it'll become 3.79245. So that's the number that goes in the first box. So in the second box, it's always 10 to the power of something. In the second box is how many places we moved the decimal point. So here we moved it 3, 6, 9 spots. So a 9 goes there. So this is just saying the number is basically 3.79 billion. So if we were asked to round that to significant figures, it's sort of like rounding to decimal places, only firstly we count numbers before the decimal point as significant figures, and secondly we don't count zeros at the start of a number. So here, if I wanted to round this to 3 significant figures, this is a significant figure even though it's before the decimal place. So is this and this. We use the same rule for rounding. If the next significant figure, 4 or less, leave the mess, 5 or more raise the score. 2 is 4 or less, so we leave this as 3.79 times 10 to the power of 9. That is the answer rounded to 3 significant figures. So let's look at a really small number. So this number is obviously really small. Same process for putting in scientific notation. We move the decimal point until the number's between 1 and 10, and we get 1.86721. So it's going to be times 10 to the power of something. So the power of 10 is how many spots I moved the decimal place. So I moved it 5 spots. Now, because this is a really small number, because I moved the decimal point to the right, this number is actually negative. If the number's really large, the power of 10 is positive, and if the number's small, the power of 10 is negative. So if I wanted to make this to, let's say, 2 significant figures, 1 is a significant figure. Now, because the third significant figure is 5 or more, I raise the score. So this would be about 1.9 times 10 to the power of minus 5. So the last thing I want to do is correct a number not written in correct scientific notation. So let's have the number 207.65 times 10 to the minus 18. It's not in correct scientific notation because this number here is not between 1 and 10. So what I do is I'm just going to write this part in scientific notation. So that would be 2.0765 times 10 to the power of 2. But remember, I was timesing it by 10 to the minus 18. So using index laws, 10 to the power of 2, times 10 to the minus 18, keep the same base, add the powers. 2 plus negative 18 is negative 16. and then I keep this number in front. This is written in correct scientific notation. It's a number between 1 and 10 times 10 to the power of something. Now note this number here and this number here, they are the same number with the same value, but this is written in correct scientific notation. Alright, thank you so much for watching this. Best of luck in the test. You're a superstar. You will ace it. First 5 people from my class say Caramello Koala. 1 is all yours. Thank you so much. This has been the luckiest maths teacher in the world. Have a great day.